Hello, my name is Dr. Tanya Simuni. I am A.C. Nielsen Professor of Neurology and the head of the Division of Movement Disorders at Northwestern University, Chicago. And it is my distinct honor and privilege to interview Dr. Surmeier at the 21st International Movement Disorders Congress.
My name is Jim Surmeier. I'm chair of the Physiology Department at the Feinberg School of Medicine at Northwestern University. I'm also director of the Morris K. Udall Parkinson's Disease Center of Excellence at Northwestern.
Dr. Surmeier, I will be asking you, what was your path to your incredible career in neuroscience and specifically your dedication to Parkinson's disease? So tell me about your early years.
My goodness, it sounds as though my career is over. So
that's not what I implied.
I hope that that's not true. So, yeah, I was raised on a farm in Idaho. There was no expectation that I would go to university. None of my family had gone to the university. My guidance counselor in high school actually recommended that I think about welding as a career.
That's an interesting...
Right. And then I scored a 1,500 on my SAT, and he thought I should go to community college. So...
You exceeded the expectations.
I exceeded their expectations. And so I ended up going to the University of Idaho because it was close, and they offered me a scholarship to go there. I studied mathematics as an undergraduate, but really enjoyed the undergraduate experience. So I was close to a major in several other areas, including English and political science. At the end of my undergraduate career, I did not want to go back to the farm, so I entered a graduate program in mathematics, PhD program in mathematics. And in the second year, I got interested in neural networks. And it struck me as a mathematician that the neural network models were not very well constrained, and so I decided to take a short leave and go to the University of Washington, which was close by in Seattle, and see if I couldn't work to constrain some of the models of brain networks that were being constructed at the time. I was there for a short period of time, and they asked me to join the PhD program in physiology and biophysics, and it was a great program, and so I quit the mathematics and continued with physiology and biophysics. Got my PhD there. I had a very grand notion of what I was going to do. I had decided that I really was going to try and understand how the brain worked. I've been disabused of that idea over the course of the last 30 years, but it gave me an opportunity to study systems neuroscience, and I did my first postdoc in systems neuroscience, studying mostly pain signaling. Interestingly, I like to tell this story particularly for students. It was a disastrous postdoc. I hated the work. The hours were long. The work was not intellectually satisfying, and I had decided to quit. And I had actually started writing applications to law school. And it just so happened that at that time, a fellow by the name of Steve Katai came by the University of Texas and gave a seminar. And he and I had met when I was a graduate student at the University of Washington. And he asked me what I was doing. And he said, I told him, I said, I'm leaving. I'm going to go do something else. And he said, stop. You've got this much invested. I'm setting up a new group in Memphis, Tennessee, of all places. I want you to come. Spend at least a year and see if you can't rekindle some of the excitement that you had as a graduate student. And I thought, well, you know, what have I got to lose? And he told me, he said, you know, I'm interested, again, in the basal ganglia, and I'm particularly interested in what dopamine does. He said, come and work and try and tell me whether dopamine is excitatory or inhibitory. And I went and fell in love with the basal ganglia and with trying to understand what dopamine was doing, and my career in studying that part of the brain and studying movement disorders sort of took off from that.
So, interesting path from math to systems physiology, short of law school, and into the 30-year illustrious career of trying to understand the pathways of the basal ganglia. So reflecting on the career, obviously mentorship and the right mentorship plays tremendous role. So who are your heroes?
Yeah, well, I mean, Steve Katai is certainly one of my heroes. I mean, he taught me to be irreverent, taught me to think about things in a way that reflected my background and my training rather than necessarily all the other people around me. I think he also taught me that, I hate to use this metaphor, but it takes a village. And one of the things he did in Tennessee was he created a group of people, young people who were working on similar problems, who had complementary interests, and it was really out of that interaction that most of my understanding of the basal ganglia and of Parkinson's disease, at least in the early phase, arose, right? So I think that that having colleagues to interact with is certainly important. It's one of the things I strive to do as a chair of a department of physiology. Another hero of mine is Paul Greengard. I've worked with Paul for a long period of time. Soon after I became interested in what dopamine did in the brain, how it modulated neuronal excitability, I got connected with Paul, and he's been a huge inspiration for me. I mean, he's one of the greatest minds I've ever met. He's tireless. He's now in his early 90s and still doing science. And I continue to collaborate with him. And he's a free thinker. He's somebody who's not afraid of challenging conventional wisdom. And I think that that's really important.
Tremendous. So reflecting on your career, that obviously is not over, what is the greatest achievement?
Oh, time will tell, won't it? I mean, I spent most of the time since starting work with Steve trying to understand what dopamine did to basal ganglia circuits, how it modulated the activity of neurons, how it shaped how they integrated information, and how it led to long-term memories. So I think that certainly the bulk of the work that I've done is pertinent to that question. And it goes back to the whole idea that Steve posed when I originally went to work with him. He asked me whether dopamine was excitatory, inhibitory, and again, he was thinking about dopamine like a classical neurotransmitter rather than a neuromodulator. And I think that one of the achievements I've had in my career is to push the idea and convince people that, in fact, dopamine's actions can't be boiled down to a plus and a minus sign. That, in fact, the actions are more complex and more subtle and nuanced than that, and that's important to how dopamine works in the brain. And how we have to approach disorders like Parkinson's disease where the loss of dopamine is a primary driver of pathophysiology. Obviously, the other major thing, and the thing that I'm probably best known for at MDS, and the thing that we're partnering on, is trying to understand the etiology of Parkinson's disease and what is it that causes the loss of dopaminergic neurons and other neurons in the brain. And this is a little bit of a funny story. I tried for years to get friends to tell me what was different about dopaminergic neurons. Why were they particularly vulnerable in Parkinson's disease? And they would always smile at me and say, gee, that's an interesting question, Jim. Why don't you go pursue it? We have our own agendas, right? And so it was maybe 15 years or so ago that we finally decided to bite the bullet and go and use some of the techniques that we have at our disposal to try and answer that question. And that led to a completely new line of research for us and for me. One of the great things about being an academic is that being able to chase ideas and pursue ideas that excite you and interest you. And so obviously that work has led to the hypothesis that the design of dopaminergic neurons, the role they play in the brain, the way they control not just electrical activity, but the way in which they use that activity to control their bioenergetic systems is a main driver of pathogenesis, that they wear out with time. And that's led to the hypothesis that inhibiting L-type calcium channels could lower their mitochondrial oxidant stress, could lower the general stress level on these cells and make them last longer. And it's led to the phase 3 clinical trial that you're leading. So obviously, if that trial succeeds, that will be my single greatest achievement, I think, and it'll be the thing that we're known for. So, but time will tell, won't it?
Certainly. And I certainly can say that for me, our collaboration and the experience of taking the molecule from well-characterized physiology and rationale to the early clinical trials and to the phase 3 clinical trial has certainly been the highlight of my career, independent of the results of the study. But speaking of, what have been the greatest challenges in the path?
That's actually a very difficult question. I mean, there are lots of ways in which it can be interpreted. I think from a scientific standpoint, the biggest challenges I've had are grappling with the initial results, maybe with the experiments that we did, trying to understand why dopaminergic neurons were vulnerable. So it led us in a direction that I hadn't been prepared to study. So and let me try and explain that more clearly. For most of my life, as an electrophysiologist, I had stuck 2 millimolar ATP in my patch pipette and never thought about bioenergetics, for example. It was very clear from the work that we began to do using optical techniques to image organelle function in vulnerable neurons that bioenergetics was central to the events leading, we thought, to the death of dopaminergic neurons. Mitochondrial oxidant stress rose in response to calcium entry through these plasma membrane channels. But figuring out why that was and what the mechanisms were underlying it was a huge challenge because as an undergraduate, I didn't take any biology classes. You
were in mathematics.
I was in mathematics, and so it was a great challenge, intellectual challenge for me to be able to establish some kind of link. And again, this goes back to a point that we made earlier. It takes a village. So I set up a collaboration with somebody who works on the heart, where the bioenergetics are much better studied. We've had lots and lots of extensive discussions with people in the Cancer Center. Again, people who study bioenergetics, and I've been able, over the course of the last decade or so, to learn a lot about how that might work in neurons, although I still think it's a huge gap in our understanding. So there's been that scientific challenge, and getting people to at least give the idea that bioenergetics might contribute to pathogenesis in Parkinson's disease, get them to give it at least a few minutes. I mean, obviously, this is not the predominant theory of pathogenesis in Parkinson's disease. People are much more comfortable with the idea, for example, that alpha-synuclein pathology and protein aggregation are drivers of pathogenesis. And I think getting your ideas, getting this idea out there, getting this idea to be discussed, at least, has been one of the major challenges. I think that's probably in the last decade, that's been the biggest challenge I've faced.
I'm not done with the challenging questions. And speaking of the last decade, looking forward, where do you think the field is heading in the next 10 years?
No. You know, for a lot of the things that we do, advances are driven by technology. So about 15 years ago, I became chair of the Department of Physiology. I had worked for 2 chairs. I had no interest in being a chair because I saw what it did to their scientific lives. And I love science too much. I really wanted to continue to do science and not do administration. But at that point in time, a technique called 2-photon laser scanning microscopy had been developed. And it was clear that that technology made accessible to me as an experimenter dendrites and synapses of striatal neurons, basal ganglion neurons, and that was clearly where dopamine was acting. And previous to that point, I had been doing mathematically very precise quantitative measurements of the dopamine actions in the cell body, which may or may not be relevant to what was going on in the dendrites, where 95% of the dopamine receptors are. So the development of that technology opened that door to us. And so I think that's led to huge advances in our understanding about how dopamine is regulating neuronal activity. And there are continuing to be advances made in that area. So one of the things that's happening now is that there are huge advances being made, I think, in 2 major areas. One is related to the optical approaches that we use to image not just things like intracellular calcium, but organelle function. And those technologies are opening up areas that are really critical to pathogenesis, for example, axon terminals, dendrites where synapses are. We can now image mitochondrial function, we can image lysosomal function, we can image the function of domains that are really critical to pathogenesis. So that's giving us a microscopic view of pathogenic mechanisms that are important to identifying molecular targets for drug intervention or genetic therapies and things like that. In particular, I think neuronal bioenergetics is going to just explode with this. This is a part of brain function that we really don't understand very well. I mean, how do neurons manage their energy demands? What's the balance between oxidative phosphorylation and glycolysis? How do they anticipate demands? Because we know that meeting those bioenergetic demands is not only crucial to proper neuronal function, but it also is something that goes wrong in many disease states and is a primary driver of pathogenesis. And we just don't know really very much about it. The other major area where technology, I think, is having a huge impact is in understanding systems, large-scale neurosystems. With the advent of the BRAIN initiative, we have all these new tools for mapping the connectome of genetically defined neuronal populations. Again, one of the huge problems in the brain is the complexity, the cellular complexity, the molecular complexity, and we need to be able to tease that apart, and these tools are giving us the ability to tease that complexity apart and understand how the wiring of the brain contributes to the computational capacities and how it goes wrong in disease states. We've also got new physiological techniques, optogenetic techniques, chemogenetic techniques that give us the ability not just to understand what cell type is connected to one other cell type, but also how they work together, how they function together. And I think that in the future, in the not very distant future, both optogenetic and chemogenetic tools are going to make their way into the clinic. These are ways in which we can manipulate in a controlled way complex neural circuits that may become dysfunctional in disease states like Parkinson's disease. I think that that's going to create a huge opportunity, not just for understanding normal neuronal function, but also to understand how we can correct pathophysiology in disease.
So you remain excited and infused about the future, right?
Yes.
So shifting the topic, as a chair of the department and as a very visible and prominent figure on the international neuroscience arena, I'm sure that you're frequently asked the questions by the people entering the field. So what is your best advice to the young scientists?
You've just said it. I think the most important thing is to be passionate about your work, to find something that you love to do and to chase it. I mean, the work has to be fun. The work has to be exciting to you because although the clinicians make extraordinary amounts of money for what they do,
that goes on the record.
the basic scientists we get paid reasonably well, but not so well. You really have to love your work. And the other thing is that, so in my mind, discoveries and real breakthroughs come from two things. One is passion. You have to be passionate about your work. You have to think deeply about the problems. And you have to have colleagues, you have to seek out colleagues that you can talk to. And particularly seek out colleagues that don't necessarily agree with you, right? Because I think, for me at least, the greatest discoveries that I've ever made, I think, have come from an interaction. They've come from a dialectic, some give and take where a friend or a colleague has pushed me to a place where I could see connections that I wouldn't have seen otherwise. And so it's one of the reasons why societies like the MDS are really important. I mean, in particular for me, because, again, I'm a mathematician, sort of basic scientist, and having the opportunity to interact with clinical colleagues who have very different perspectives and approaches to the problem has been really critical. I mean, I look at our interaction over the course of the last decade or so, and again, from my standpoint, it's been one of the most rewarding and productive interactions I've had, and it changes the way I think about problems. It changes my focus, and I think that's how you create relevance. That's how you create conceptual breakthroughs that affect a lot of people, not just some tiny little subdiscipline, right? So I think that for young people, that kind of you have to do what you do as well as you possibly can, but create a perspective, create a context for what you do, and I think it helps sustain your own passion, and it'll also get other people engaged in what you're doing because you're reaching out beyond the little tiny domains that you would otherwise.
So you started talking about the role of the society in your career. Can you expand more? What has MDS, how has MDS contributed to your career? And what is the greatest collaboration within the society?
Okay, so MDS has been very helpful to me in a number of ways. I mean, one is to give me the opportunity to interact with colleagues who have got a more clinical perspective, and also with basic scientists who are translationally oriented like I am. I mean, I know the society is continuing to try and increase membership among translationally oriented scientists that are not clinicians, don't see patients. And that's been extremely important to me. I mean, for example, let me give you an example. So recently we just published a review in Nature Reviews Neuroscience that addressed the hypothesis that Parkinson's disease was a prion disorder, or at least re-examined the question about to what extent does spreading of a pathology as opposed to cell autonomous factors dictate the situation in Parkinson's disease brains. There were 3 authors on that. I was one author, Glenda Halliday was another, and Jose Obiso was another. That review was a product of us sitting in the back of a room at an MDS meeting several years ago, struggling with the ideas about that had been just presented in a lecture about pathogenesis in Parkinson's disease. That would not have happened had I not been at an MDS meeting. And from my standpoint, having Glenda and Jose clearly map out in a way that I could understand the clinical scenario, the human pathology was critical to me going ahead and making an argument about what the cellular mechanisms might be. I mean, that created a context that I individually could not have created otherwise. And as a consequence, I think the review is a much more important piece of work than it would have been otherwise. So that's a direct consequence of the interactions I've had at MDS. And the other thing I have to say about MDS is MDS has encouraged me by giving me the opportunity to speak. They've also encouraged me to continue to push the translation of basic science discoveries, not just in Parkinson's disease, but in other areas like dystonia and Huntington's disease. And I think that encouragement is really important, particularly for basic scientists, because it's all too easy for me to slip back into studying ion channel biology or spike generation and not think about how that translates to the broader clinical picture. And I'm in debt to them for that.
So far the conversation has been obviously about the career, about work, and an interview like this cannot go without the question of life-work balance. So does such exist?
No. Well, you know, I struggle with this. And my wife certainly doesn't think that I have a reasonable balance between work and life. I mean, I love my work, and it's hard to keep it from creeping into my personal life. And at some level, I don't want it. I want it to. I want my kids. I have 3 boys. I want them to see that it's possible to have a career that you love and enjoy, right? And I don't know what it's going to be for them, but I hope that they find something that they have passion about. But that said, I do have to try and create some balance, and so I do try and set aside blocks of time, particularly around the kids' school breaks and over the course of the summer, where the number of the hours in the day that I think about or am reading or writing is restricted, and that I focus entirely on them.
So there is a balance. There is just different threshold for balance, right?
Right.
Let's put, and I guess my last question is a rhetorical question, but I have to ask it. Have you experienced biases and barriers? And that is a rhetorical one. And what would you tell your junior faculty and your trainees how to handle them?
All right, I thought about this question, and my response was not any barriers that I paid attention to. I mean, I obviously am a white male, right? So the gender barriers, the racial barriers are not ones that apply to me. I guess now that I think about it, though, there is one barrier. I'm a farm kid. Most people think farm kids should stay on the farm. And so when I guess the only bias that I've encountered is, but this is obviously a little bit of a joke, is that how is it that you made it through? I was the first person to go to university in my family. I went on to get a PhD and have had a successful academic career, but didn't have the back pressure to do that. It came more from me than from any family pressure I had. But the bottom line is that I think that I've been blessed. I really have not had to deal with any serious biases or barriers, and I'm grateful for that.
Again, you could not have said it better. The drive came from within. And I think that this is the best notion to give to the next generation. The drive has to come from within. And I could not have more eloquently communicated the enthusiasm, the energy, the commitment, the dedication. And I will repeat again that our collaboration has been the highlight of my career so far.
It's been terrific for me as well.
Thank you.
Thank you.